Hi, good evening. So, am I audible?
Yes, sir.
Okay, thank you. I so we'll just start in 2 minutes. So, what we'll do is uh, we'll kind of go back and forth between the coding part and the theory part. So, there is some theory part that is remaining, which we haven't covered from the naive base regarding the naive base model. So, I'll just quickly go over it, and then if it becomes too much of mathematics, then we'll briefly abandon this theory part and start doing the coding thing, right? So okay, so while the others join, if in case others are joining, we'll let's not wait anymore. We'll get started. So what we were looking at, this problem of text classification on Monday, right? So how do we understand the naive base model with this example of text classification? So the problem that we were looking at was spam versus ham. So you're given a set of messages, and you need to classify them as spam or ham, right? So spam is the spam we are all familiar with. Ham is just a normal good message, right? So that was our problem, and so the approach that uh, we are going to study is naive base, right? But before we go there, we need a way to convert our text into features, right? Because everything that we have done so far has been with the feature matrix, m cross n feature matrix. But what we have is just text words. So we need a way to convert raw data to features. And this process is called feature extraction. In the case of text data, feature extraction can be done in many ways. One of the ways is called a bag of words approach, right? So let's say we have a message like this. What we do is we extract the frequencies of the words, ignoring the order or sequence in which they occur. So in this particular message, all these words occur once, and the word free alone occurs twice, right? So the order is thrown out, but the frequency is retained. Now, given the frequency, what we do is we represent each message as a vector, right? So if there are, say, 10,000 words in your vocabulary, then you have a vector of length 10,000, and a message is encoded as a vector of length 10,000 with zeros in most places, but the frequency of that particular word which occurs in that message, that will get displayed here, right? So for example, in this particular message will be represented using this vector of, say, length 10,000. Okay, so that is the bag of words model. Once we have the bag of words, yeah.
Just a quick question. So when you say a message, that means the entire body of the email. Is that if it's a spam, the entire body of the email, or is it normally typically the subject? Just to understand how what gets processed.
Okay, yeah, that's a good point. So that it depends, right? So now that you ask this question, I think I'll probably process. I'll probably have the subject also, because sometimes subject is more than enough to tell if a message is, identify if a message is spam or not. But I'll have the body and say subject. Right. So since anyway we are only the order is thrown out. So you can just think about all the words that are present in the subject as well as the body of the mail.
Okay. Okay. Thanks.
Okay, so if you have n such messages or documents or mails, then you represent each as a vector of size m, right? And therefore you get this feature matrix n cross m. Okay, so this is where our techniques begin, right? So now you can apply any standard ML technique to classify this as spam or ham. And yeah, so the approach is to use base rule. So finally, what we need is, given a message, is it spam or not? We have to find this probability. So for a particular message, it will look something like this. You use the Bayes theorem. So we need probability of message given spam, right? And this is where we use the naive Bayes assumption, where we split all the words into individual probabilities, right? We use this conditional independence assumption and we convert this probability into a product of several probabilities. So this is the naive Bayes assumption. Okay, and similarly, we do this for ham. And whichever of these two is greater, we say that it belongs to that particular class. Okay, so the only question here is, how do we estimate these individual word probabilities? What we decided that day was that we will do it simply using the frequency, or how often does the word free occur. It occurs 2000 times in the spam. Among all spam messages, 2000 of them are free. So the probability of free given spam is 2000 divided by 100,000, assuming there are 100,000 words in the spam class, right, overall. So this is, I'll skip the smoothing part. So this is where we stopped that day. And so this, if you remember, I said that this is a good heuristic. So why should this work, right? And why does this work? So that's where we stopped. So I hope you all have the context now and I can move forward. Is that, are we clear on that?
Yes, sir.
Okay, right. So this part is important because if you want to understand the content for week 6 as given in the slides, then this notation will be of some help. So please pay attention to this part. There'll be several symbols coming up. It is unfortunate that we have so many mathematical symbols, but we have to live with that. So superscript, if you recall, the convention we have been following will represent the index of the data point, right? So this is the ith data point, and this is the label corresponding to the data point. So there are n such messages. Okay, and each message is represented by a vector of size m, right? So m features. In this case, each feature will be some integer, right? So xj, for example, will be the frequency of the jth word, right? Or how many times word j occurs in that message. Okay, so if you get lost, then please make this connection between the text classification example that we are doing and the symbols, right? So x1 is the frequency of the first word in the message. So this is what x represents. And assume that we have k classes, right? Instead of just 2 classes, spam or not spam, let's just take the general case of k classes. Okay, so this will be our notation. Now, okay, so we need to learn several parameters, right? So if you recall, we what we want to do is we need to learn the probability of word given spam, right? And word given ham. So it's like P of xj given C is what we want to learn. So is this part clear? So do you all get what I am talking about here? This WJC is one parameter for a probability distribution. So is that clear?
So could you repeat that please again? Okay,
so see, what we want is we want to find this probability, right? Word, we want to do this for every word, right? If there are, say this is the ith word, I really want to estimate what this probability is from my data. Now, using my notation, what this basically is the probability of the jth word, right? Probability of seeing the jth word given class C, right? So the C could be spam or ham, right? But I am generally calling it WJC. In fact, I'll just be more explicit. This is the probability that I'm interested in. How likely is it that this message contains the jth word, and given that the class is spam?
So in this case, we have only two options for that Y, which is spam or ham. So basically that vector K is two. I mean, it has only two dimensions.
Yeah,
right? One, two.
Right. In this case, it will be 1 to 2. But assume that there are like K classes.
Yeah. Got it. Yeah.
Okay. So this matrix, what it means is that this is what it means. So what is the probability of the jth word being 1? Sorry, jth word occurring in this message, given that the class that it is coming from is C, right? So what is the probability of seeing the word free given spam? So that is what this WJC means. Okay, and if you have M words in your vocabulary and you have K classes, then there will be K into M parameters, right? So each one is a parameter. Okay, so this is the notation. I assume that you have all got it and I'm moving on. Yes, yeah. So Afnan, you have a question?
Yes, good evening.
Yeah.
So here we are giving xj as 1, right? So isn't it taking into account that there could be more than one words also, given that this is a frequency?
Correct. Good point. I'll come to that. So you are right. But for now, just assume that this model's presence or absence of a word.
All right, sure. Yeah.
Okay. So for now, assume that this is presence or absence. So if you know, think about it, what we are talking about is this scenario. Think about an M-sided dice, right? You have a dice and there are M sides to it. So each side, one word is written on each side of this dice. Okay, so what is this WJC? It is nothing but when you throw the dice, right? What is the probability that the jth face will come up on that dice? Okay, so assume that there are only 6 words. Take a standard dice and your vocabulary has only 6 words. Then this WJC will be the probability of one of the, say, the jth face of the die coming up. Okay, so this is actually what we call a categorical distribution. Okay, is this mapping clear between the probability and this category and the distribution?
Yes, sir.
Okay, right. So this is categorical distribution. So now can you tell me what this sum should be?
This is actually adding up all the words, the number of times they occur.
Okay, so see, W in this case, W is a probability, right? That we have to. So W is a probability, WJC. So if I add all these probabilities for the M words for some class, what do you think will come up?
1.
Right. So this is, yeah. So how do you, another way to understand this is if you throw a dice with M faces, at least like some face has to come up, right? So like if you toss a coin, either heads or tails has to come up. So if you throw a dice, then one of the M faces has to come up. So this sum has to be 1. Right. So in terms of this matrix, what it means is every column, if you add all the numbers, it should be 1. The sum should be 1. Okay. So the reason any question at this stage?
So it's slightly out of the way, but if you could explain when we add columns in Numpy, is axis taken equal to 0 or 1? I always get confused in that.
Axis you take it as 1, right? So axis equal to 0 will be the row, So you can have this in mind. Axis equal to 0 is the rows.
Okay.
You are looking at the row, and 1 is column.
So in this, it will be 1. Axis
It will be
equal to
1. Axis equal to 1.
Okay, right.
Okay, so
but sir, when we take NumPy mean, it is the other way around, right?
NumPy mean, okay, so I think it is good to go back and forth. So let's take okay, so this is NumPy. Let's take this example of 1, 2, 3. So this is the matrix, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. And so when I say X, when I sum this along axis equal to 0, let's see what we get. So we get, oh, what do we get? We get the, okay, I was wrong. I think
no, so actually the problem is, I mean, this is actually an intuitive understanding only. Axis 0 is really rows only, but the thing is, because we look at this vector like a matrix here. See, technically 1, 2, 3 have to be written straight. If you write it in a matrix form, 1, 2, 3 is written straight. Similarly, 4, 5, 6 is written straight and vertically. And similarly, 7, 8, 9 is written vertically. If you write it in matrix form. And then if you actually do axis 0, you're actually adding up across rows. So 1, 4, 7 is actually in a row. 2, 5, 8 is in a row. 3, 6, 9 is in a row. And that is the answer you're getting here.
Okay. Oh, okay. So this is...
No, what I'm saying is, because we are looking at NP array as a... It's in the second axis, right? 1, 2, 3 is written in a second axis.
Right. You are right.
So which means, I mean, if you write it in paper, you're actually writing it as 1, 2, 3 as vertically, 4, 5, 6 vertically, and 7, 8, 9 vertically. That is how we would write a matrix.
Right. Yeah. So this is a good point. I think these are the kind of things which I think we get. So if so you're saying that the axis equal to 0 here.
It refers to rows only. It's basically adding across the first dimension or a 0th dimension in this case.
Okay. So yeah, so this is a good point, right? So just give me some time. We will discuss this in more detail. I just want to
discuss. Sir, because I'm still confused.
Okay, right. So we will take Kaushik's help after some time. So
right, sir.
Until then, we will. Yeah, but this is good. I think these are the kinds of things we'll get. Let's try to clarify it in this session. Okay, so
just one question here in this, just trying to understand this dimensions of this one. So x1 through to xm are features, as in basically the frequency of words, right? In one message.
Are the right.
Frequency of words in one message. So I'm assuming the learning data, the training data will have many messages like that.
Right.
So that is a separate dimension by itself, right? So meaning you'll have multiple multiple instance or multiple samples of M features, and each of those each sample will have K what do you call it, classification or whatever that WJC is, 1 to K is. So I'm just trying to understand the training data, the way it will look, because you'll have multiple messages, right?
Yeah, so the training data will look, say, I mean, let's repurpose this for the training data. So it looks something like this. Say if there are only 3 words in your vocabulary, so it will look something like this, right? So this is too symmetric. I don't want it to be so symmetric. So let's say we add one more dimension or one more example. So there are 4 messages here.
Right.
Right. And see, after that row sum, I'm kind of confused. So this is 4 cross 3, right? So there are 4 messages. Correct. And each message is represented by this vector, one such vector. And so this third message here, for example, means that the first word occurs once, and that's all. There is only one word in that message.
Right.
Right. So this is
right. And so for each of these messages, for each of these messages, you will have 1 to k classes.
Yeah, you will have one of these. Yeah, one of these k classes will be assigned to that.
Right. Okay.
Okay.
Sir, I also have a doubt. Sir, in the first row it is mentioned 102, and in the second row it is mentioned 300. So that means the same word came in the first row once in the first position and 3 times in the second statement. Is it like that?
Yeah, in the first message, the first word occurs once and the last word occurs twice.
Okay.
Right. Whereas in the second message, second training example, first word occurs thrice and no other word occurs after.
The same first word which was in
same
the
first word. Yeah. So for example, the words could be free, money, say something, holiday, whatever. Right. So in this case, the messages would be free, holiday, right? In any order, could be in any order, but
yes,
that would be the first message. Whereas second message would be free.
That will be free.
Right. Right. So that is what we are. Okay. So that so far I hope it's clear. This is the next question, right? So if a message from class C occurs 2 times, right? So for example, if a word, what is that word? Let's say this example, right? So the second example will be what? Free, right? So in that case, what will this probability be?
It will be 2 by the total sum of the matrix for that particular class. For that class.
Okay, so we already know that the probability of it occurring once is WJC.
Right.
So what is the probability of this word occurring twice? So in an experiment, you toss a coin twice. So probability of 2 heads
will be
squared,
right? So right. So it's like the same dice, you are throwing it twice. So it's like WJC squared. So this is the question I think Afnan you are asking, right? So if the word occurs say whatever number of times, this will be WJC power the number of the frequency.
Yes, sir. It's correct now. Yeah, sure.
So so every document is like a toss.
Every document is like a toss of a so this is the question, right? So in general, XJ is the number of times the jth word occurs in a message. So how many rolls of a dice are required to generate one message?
Hello, sir. Hello, sir.
Yeah.
Sir, can you please repeat the last word, that WJC part?
Yeah. So the WJC is probability of seeing the jth word if given this class.
Here class means we are clustering is in each word in some kind of class, and
not every word. Every message is either in spam or ham. One of the 2 classes. So every message, right? Not every word, every message. Yeah. Okay, so right. So let's go back to this example. So if you have something like this, if you want to generate this message using this distribution, how many times should you have to throw this dice?
3 times.
3 times, right? So that is all this is saying. So if you sum xj over all the m values, then you have to roll the dice that many times. Okay, so this is nothing but the total number of words in that example. Okay, so assuming that you have understood so far, then the probability of seeing a message given a class, right, given spam, is nothing but product of individual word probabilities, right, power their frequency into some count. So can someone tell me what this count, why I have added some count here?
Is it because we have two classes, that one spam and ham?
No, right, because I already fixed the class. I already condition it on a particular class.
Is it like smoothing or something?
Not really smoothing, but okay, so think about the dice, right? So I throw, okay, let's go to numbers instead of words. So I throw a dice 5 times, and these are the numbers that come up. 1 0 3 4 1. Okay, so what is the, so this will be what, W1 power 1, W2, so say 0 1, it's a 5, it's a dice with 6 sides, right? So 6-sided die. So my probability will be what, W1 power number of times 1 occurs, W2 power number of times 2 occurs, and so on, right? So let's say this is 3. Now can you tell me what this count actually would mean in this case? Okay, so this count takes care of the ordering, right? So this 1 3 3 4 1, I can get it in several ways, right? So I can get it as 4 1 3 3 1 1 3 4 1 3. So I need some way to keep track of the count. So that factor is what this count represents. Is it clear or is it very confusing?
Not clear. Are you saying it's the permutation of all the?
Exactly, yeah.
Okay.
It will be combinations actually. And choose, yeah.
Yeah, it's slightly more complicated than a simple combination because you'll have to keep track of repetitions. But yeah, that's the idea, right? So see, don't worry too much, but all this is there in the slide. So I need to justify where this comes from. That's why we are doing all this work.
Can you just go a slide before this? This before. Can you please explain this sum again? Just one more time. How many rows? Yeah.
So see, think about it as a generative process, right? How do I generate a message? Now, let's say I want to generate a message using this distribution. What I will do is I will roll the dice. Say I want a message of length 7. I want 7 words.
Right.
Okay. Then I'll roll my dice 7 times. And so when I roll it the first time, let's say the third word comes up. So then x3 equal to 1.
Right.
Right. So I'll just be a little more explicit. Otherwise, it'll be very tough to follow. So free money, good. So let's say this is our vocabulary and it's a 3-sided die. I roll it 5 times. I roll the dice 5 times.
Right.
So first time money comes up. Second time also money comes up. Third time free. Say fourth time free, and fifth time also free. Okay, so this is my generative process. I've used the probability distribution I have in my hand to generate a message. So the message will be, in this case, this will be my message.
Right.
Right now I'm working backwards. What I'm saying is, for this message, x, say this is x1, x2, x3. x2 equal to 2 and x1 equal to 3. So x1 equal to 3 because free occurs thrice. x3 equal to 0. right? So what I'm saying is, if I want a message like this is what vector 3, 2, 0. So if I want to generate this particular vector, which is a message, I need to roll the dice 5 times, is what I'm saying.
Okay. Okay, sir.
Okay, so that is what this expression means.
Okay.
And now, just to extend that, in order to get that once, get say money once, what we are saying is we are calculating the frequency as a probability and to the power 3. Is it? That's how we are going.
Yeah.
Like we are taking it from the bag of words, the frequency, and then calculating the probability from that, and then to the power 3 will give me the probability of getting money 3 times.
3 times, yeah.
Okay. Thanks.
Okay, so that is what this means, and this count is assuming that there are L words in your message. L factorial is all possible permutations, but there are repetitions. So the first word occurs x1 times, mth word occurs xm times. So you divide that by x1 factorial, xm factorial. So this is basic permutation combination. Don't worry too much about this count because you can get away with this count, right? What is important is this term on the right hand side. The word probabilities power their frequencies. That is the main thing. Okay, so this is what is called the multinomial distribution, right? So if you have seen the slides for week 6, in one of the slides, this thing will just magically appear. Okay, so this is the rationale behind the distribution.
And so just to confirm, WJC includes, it's actually probability of that particular class multiplied by probability of that word occurring given that class, is it? That's what WJC is, right?
WJC is the probability of this word appearing once given a particular class C.
Oh, that's all. Okay. We still have to multiply it with the probability of that class.
Yeah, that is the P of Y that we have not yet come to that part. So that will come in a while. The next slide it will come, right? So this is, we are now modeling the conditional distribution, that is class conditional distribution of the data.
But sir, why do we do a product of all of them? Why WJC, sorry.
See, that's because they are all IID trials, right? They're all independent.
Okay, yeah. This is the first assumption that we made.
Yeah. So the naive, because it's naive, I can break down P of X given Y as P of X1 given Y into P of X2 given Y.
Yeah.
Right. So, so much for the multinomial. Now what we have to do is we have to estimate the WJC. So remember that very crudely what we said was WJC is the number of times the jth word occurs divided by the total number of words in the Cth class or class C, right? So we have to mathematically justify that. That's what we are doing. That's the whole point of all this. How do we do that? We use maximum likelihood estimate, right? So MLE. So MLE is what? It's just this product of all the probabilities. This is the joint distribution P of X comma Y. You multiply it for all n messages in your data set. You just use basic rules of probability. This is prior into P of X given Y. Okay, so converting from likelihood into log space, you get log likelihood. So product becomes sum. So this is, all this is just basic arithmetic, algebra. So nothing much here. Now we have to maximize the likelihood. Okay, so maximize the likelihood. This prior term we can ignore. Okay, so prior, the likelihood, if you notice, doesn't depend on the priors. It depends only on how we choose to model P of X given Y, right? So you can get rid of the prior term. So you end up with this expression. You have to maximize L of W, where this is the form it takes. Is it clear till now?
Yes, sir.
Okay, so see, so far whatever I have written is true for any distribution, right? Now P of X given Y, what it is, how does it look like for a multinomial distribution? This is how it looks. So instead of P of Xi given Y, I'm going to substitute the expression for the multinomial distribution, which is this. So this is a very hopelessly complicated expression, but what this is actually WJC power Xj. Only thing is that instead of C, I'm using Yi, right? the yi is nothing but the
Label.
label for the ith data point. xji is nothing but the frequency of the jth word in the ith data point. So I have just started that superscript corresponding to the ith data point. That's all I have done here. So this is just wjc power xj. Okay, I hope this is also clear. Now, if you plug this into the log likelihood, this is what you get. Okay, log count plus summation, product becomes sum, exponent comes out, and then log of the probability, right? Log of the parameter that you're trying to estimate. Okay, what I'm doing is I'm just plugging this there. Is this transition clear, or slightly it can be complicated? So see, this summation is from I equal to 1 to n. Log of p of xi given yi is this, right? I'm just plugging this there. Is this clear so far? Like, this is the final expression that we have for the log likelihood.
No, where's the log count?
Log count gets eliminated, right? Because the reason is it doesn't, the weights do not influence the counts.
Right.
We are trying to estimate the weight. So when we try to maximize or minimize the weights, the loss, when we try to maximize the function where w's are the parameters, this count doesn't matter.
Right.
Okay, so that is why the log count disappears.
So we got another summation.
Yeah, so why this double summation is because outer summation is for the n training examples. The inner summation is for your m features or m words in our data set. For each example, you have m words, right?
Right.
So m features. So this inner summation, think about it this way, like your probability is what? Product of the m probabilities, right? For each example, that product becomes a sum.
That's clear, but why is it not coming in the previous expression?
So see,
okay, it's there.
It's there. Only thing is that because we take this log, the product becomes the sum.
Right.
Okay, I know this is very ugly looking, but yeah, we have to deal with this. So is this clear? I mean, even if you don't understand it completely, that's fine. But is this expression kind of sort of clear?
So can I just go to the previous slide? Just the transition from here to there, or maybe if you can just put next to each other. I don't know if that's possible.
So this is clear, right? This sum of log.
Yeah, this is clear. Just from the last one to the double summation.
Right. So
basically substituting the third one in the first one.
So this log, yeah, correct. You're right. So this third one, the third expression that you see here, right? So forget the second part. Second part is already taken care of. So
yeah.
If you forget this log count also, assume that this whole expression inside the sum is just this sum here. So log of p of x given y is sigma j equal to 1 to m x log w. And if you plug that in,
got it, sir. Yes, it's clear.
Okay. So finally, we end up with this log likelihood. So this is the log likelihood which we have to maximize to estimate the parameters. So now the question that I'm asking is this the correct formulation of the optimization problem? This is an optimization problem. You have to maximize the log likelihood. So is this correct? Is this complete? Is what I'm asking.
Any kind of constraint like a lambda?
Yeah, but why should we add that? So there's something small detail that is missing.
Need some normalization kind of thing. Right?
Constant term to make it.
You'll have to differentiate it.
Okay, let's take that route. Let's say you differentiate this, assuming that this is the correct formulation. The first thing that you do is you differentiate it. Now, if you differentiate it, what will you get? Xj is there, xj by wjc, right? You will get some xj by wjc.
Right.
Now this.
Negative?
Sorry?
Require the negative of the maximum.
That is for minimizing, right? So assuming, okay, so let's say you try to, I'll just write this loss of, this is loss in terms of W, right? This is log likelihood. And what is this? This is a double summation of xj for the ith x. Okay, this is the ith example, jth feature times the log of j. Okay, this is too big, right?
The loss or just the model?
This is the log likelihood. If you do minus L of W, this becomes the loss. Okay, so this is the loss. I mean, you can interpret this as a loss now. So the question I'm asking is this correct? So assuming that it is correct, what will you do? You'll find the gradients, right? So if you find the gradient, what will the gradient look like? Xj
by W.
Wj.
Xj by W, right? So just give me a second. Xj by Wj. There are too many subscripts, so that's why it's taking this much time. So this is 0. I get this. Of course, this won't be for the entire thing, but roughly this is how it will look like. Okay, so now if you try to set this to 0, do you see, what do you think W will be?
0.
Can this expression be 0? For any value of W, can you get this expression on the left to be 0?
Unless W is infinity.
Okay, it seems like W should be infinite.
W's are, all W's are positive numbers.
Yeah, all W's are probabilities, right? So they are all
yeah, so positive numbers. So you can't have them.
Okay, so then something is wrong, right? So there's some mistake in this formulation. I'm telling you that this likelihood expression is correct. So what are we missing? So from your MLF, right? From MLF, is this a constrained optimization problem or unconstrained optimization problem?
Constrained because Wj is between 0 and 1.
It's unconstrained.
Right. So Wj should be between 0 and 1. Okay. Is there something more stronger? Is there something stronger that you can say? Remember that there was one matrix that we displayed and we were discussing something about WJC, right?
Sum is 1.
Yeah, right. So the sum is 1. Okay, so this is a constrained optimization problem where for every class, whether it is spam or ham, all the word probabilities should sum to 1 for that particular class, right? So this is what we are missing. So since it's a constrained optimization problem, if you just differentiate that L of W and set it to 0, you won't get the correct answer. You have to solve this constrained optimization problem. Okay, so is this part clear?
Yes.
Okay, so see this I am not going into the derivation. I'll give you the link of these slides. You can look them up later. You have to do this Lagrange multipliers and all that, right? So I know you all know this, but it will be too math heavy. So I don't want to trouble you now. So finally, if you solve that optimization problem, you will end up with this expression, right? And did you all understand what these expressions in the slides mean?
So the numerator is clear, but the denominator is not clear.
Okay, right. So numerator is the number of times, the frequency basically of the jth word, right? In the cth class. So in class C, that is what the numerator is. In the denominator, what you are doing is, you are doing this for every word in every class.
So we are summing up the entire matrix, that means, sir.
Yeah, sorry. Not every word in every class. you are summing up. So you are fixing a particular class, right? WJC, let's say C spam. So you are looking at the spam messages, all spam messages, and then you are counting the number of times each of the M words appears in the spam corpus, in the spam data set. And you do that for all the N messages, right? So this is like the total number of words in the spam class.
So, sir, can we say that numerator represents the number of times that a specific word is occurring in a new sentence I have encountered, and the denominator represents how many times I encountered it in like every sentence I have seen till now, every message I have seen till now.
Right. Yeah. The denominator, what you said, I agree. But in the numerator, right? It is not just the new sentence, right? It is all the we are estimating it from the training data set. So how many times has this word, say, let's say J is free, right? J is the word free. So how many times has the word free occurred in all the N messages that belong to my spam class? Okay, it's the frequency of the word free in the spam class, and denominator is the frequency of the, it's not the frequency, it's the total number of words that are there in your spam class.
Okay.
All possible words, you say.
All possible words, right? So there is this double summation. Let's just break this. Let's break down the double summation. So first I do for all messages, right? The outer sum. Outer sum is for the N messages. Now I go inside each message, and there what I do is I look at the first word. Okay, the first word is what? X1. So in the ith sentence, what is the first word? So how do I do that? In the ith sentence or ith message, the jth word occurs this many times, right? So, and I am also interested in class C. So I add this. What is that notation? So I add this yi should be equal to class C. This is the indicator function, right? So look at all messages from class C. In that, how many times does word J occur in the ith example from my training data set? I do this for all the M words, and I do this for all the N messages.
Clear, sir.
Okay, yeah. So this is nothing but NC. Actually, it's a better notation. NC is what? NC would be total number of words in my training data set. This is very important. In my training data set that belong to class C. Okay, and this is the denominator. The numerator is close to this, but what I do is I only look at, what is the numerator? I only look at the jth word alone, not the whole. It's very confusing, man. I don't know. In exam, you have to figure out a way to do it easily. Okay, so many symbols. So numerator is what? Yeah, you look at only the jth word, right? So this is NJC. So I'll write this down. NJC is total number of times the word J, right? I'm calling this word J, occurs in my
This is also class C, right, sir?
Yeah, exactly.
Yeah, in class C.
In class.
Okay, so the English is kind of awkward, but yeah. So the final expression actually is what? The probability of seeing the jth word in class C is nothing but NJC by NC, right? How many times does that word occur in class C divided by total number of words that are there in class C. Okay, so if you remember, this is what we estimated right at the beginning, right? W free comma spam is if free occurs 2000 times in the spam class, and if there are 100,000 words in spam, 2000 by 100,000. So that is what we have derived mathematically also after doing optimization and all that. Okay, so I hope you got some idea of what this is about.
It's very clear, sir.
Okay, so that is with respect to the P of x given y, right? You also need to know P of y. P of y is, there are two ways to do P of y. You can either do what is called a uniform prior, right? If there are k classes, then the prior probability, it can be either uniform, right? 1 by k. So in the spam ham, it could be 0.5 each if you choose to go with a uniform prior, or you can be a little more informed. You can look at the data, right? So if your data has 100 messages, 70 are from spam, 30 are from ham, then P of spam will be 0.7, P of ham will be 0.3. So typically in our course, we deal with this estimation for priors. Okay, n is the total number of messages. Numerator will be number of messages that belong to spam. Okay, so
this is also got from the same data which we are training our model on, right?
Yeah. This prior and the P of x, the likelihood P of x given y, right? Both are estimated from the training data set.
Okay, sir.
Yeah, we are just using the labels alone.
Yeah, we are using only the labels, right? I am not given so the prior does not take into account the evidence or the actual features, right? It only looks at the labels.
Right.
Okay, so that is prior. So once you have estimated your W's, now how do you predict? You use base. How do you predict on a new example? You have to use base rule. Okay, so P of y given x, right? That is the that's the probability that you want, is P of y into P of x given y divided by P of x, right? The P of x, as I said, is common for all the k classes, so you can ignore them, right? So if this is not clear, what we are trying to do is at prediction time, what we want is P of y given x. This is P of x into, sorry, P of y into P of x given y divided by P of x, right? Now we have to do this for every class. So we have to do this for spam, and you also have to do this for ham. Whichever turns out to be greater, you will say that is the predicted class, right? So since the denominator is common, you leave that out. So okay, so you just compute this expression, P of c into P of x given y equal to c, right? And it's easier to work in the log space, so I have just converted this to log. So it's log P of c plus log P of x given y. And now you again use this naive base, right? So you use the conditional independence assumption. This becomes a sum. Okay, are you all with me so far?
But for the probabilities, we'll need the denominator, right?
So in this part you got, right? We don't need the denominator here.
We don't need, right?
Right. So we are just moving on from here. So instead of product of probabilities, I am just doing sum of log probabilities.
Right.
Okay. So this thing becomes a sum. Oh, okay. This probability, yeah. Okay. So now from here, see, so far I discussed about inference for a general case. Now we come to the multinomial case. So for multinomial case, if you remember, this P of xj given y is what? Wjc power xj, right? So this xj comes out. And this is how you do final prediction. So what kind of a model is this? If you focus on this part here.
It's like a regression model.
It's linear.
Right. So it is linear. It's linear in what sense? It is linear in the features, right? It's linear in the features. You could say it's linear in the log space as far as the weights are concerned, right? If you think about log W as one space that you're looking at, then it is linear. Okay, after doing all this, we end up with some kind of a linear model. Okay, so there are two other naive-Bayes models that is explained in the week. One is Gaussian naive-Bayes and another one is Bernoulli naive-Bayes. I'm not doing this now. We will postpone this to week Saturday session. If needed, we can discuss it then. Okay, otherwise it will be too mathematical and.
Sir, what do you mean by linear in log space?
So if you think about this as, so this is some constant, not constant, but I can treat this as some k, right? So let's say this is some k. Okay, k is class. So what? So let's say this is some alpha. So this is of the form alpha plus summation xj into, say I call this beta, right? Where this beta j is equal to log wj. So if you look at beta 1, beta 2 till beta m as the coordinates, then this is linear. This expression is linear in that space, right?
But beta is not linear, right?
Beta. So assume that you have made this transformation from wj to beta j, right? So assume that you have made this transition from wj to beta j. Then if you try to plot this expression in terms of the betas, right, it will turn out to be a linear function, right?
So I treat beta like a constant there.
No, beta is
coefficient.
Yeah, it's a coefficient. Yeah. So yeah, at prediction time, beta is, you can treat beta as a constant.
This kind of assumes that wj is convex in the first quadrant. Only then this becomes linear, right? Otherwise,
wj is.
It looks. I mean, only if it is constant. I mean, sorry, if it is convex within the first quadrant, by doing a log of it, it will become linear in log space.
Okay, see, what I mean by that is, this is, let's take just two values, right? Let's look at just, let's say that there are only two values. Now this is what? This is some x1 beta 1 plus x2 beta 2, right? So if I look at my prediction, this is my predictor, right? Now if I look at my prediction function as a prediction as a function of beta 1 and beta 2, it has a linear form, right? That is all I'm saying.
Right. Can you say that this equation is linear for logarithmic variables? Is it kind of that?
Can we say that it is linear in what?
It is a linear equation for logarithmic variables. Is it correct?
Yeah, in some sense, yeah. Yeah. So see, we can slightly qualify the statement. We can say that this is linear in the features, right? First of all, this prediction function. Of course, there is an argmax. So what I mean is, don't worry too much about what I meant here. I am just looking at what is there here. This log of p plus this summation, right? It is linear in the features. It is linear in the log weights, right? Assuming you transform your variables from w to log w, and in that space, it is linear in the log weights. Okay, so it's a subtle point. It's not very important, I would say. Okay, so for all the other models, Gaussian naive-Bayes and Bernoulli naive-Bayes, there is also a categorical naive-Bayes. See, I'll just give you this. We have 2 more minutes before 9 o'clock, and we can move on to programming. You just need to see this pattern for all these models. It is some numerator will be sum of something for a particular feature, and denominator will be for all items in that particular class, right? It will follow the same pattern. If you notice, this is for Bernoulli naive-Bayes, right? Instead of using a multinomial distribution, we'll use a Bernoulli distribution. So your numerator will be number of times the jth feature occurs in class C divided by total number of data points in class C. Okay, so I hope you get the general form that all these estimates will take.
So this one is clear, sir. Bernoulli's.
Bernoulli is clear, right? So this Gaussian, maybe we'll discuss it later. Gaussian is also, again, this is just a mean. Okay, if you look at it, this is just the mean of some feature vectors.
So this is basically the MLE estimate of the
right, exactly.
normal.
Yeah, this is the MLE estimate of the normal distribution. Only thing is that for each class we do the MLE estimate.
So here again, it is, if you see the spam and ham thing, here again, if it is a spam class, we are summing up in the numerator all the words, not all the words, the word that is coming, one particular word. And down we are considering all the words that are coming in the spam. It's the same thing, right?
It's the same thing. So that same formula repeats across all distributions.
Yeah.
Okay, so that is naive Bayes. Yeah, that is naive Bayes. That's the theory part. Okay, so we'll now move into the programming. I'm like kind of not sure what exactly we are going to do here, but shall we just break for like 2 minutes and reconvene?
Yes, sir.
Yeah. Okay, so see what I have in mind is something like this. So I'm going to assume that a lot of things are, and that I don't know a lot of things, which is actually true, but like about NumPy and Matplotlib, and we are going to search along the way. So this is how typically everyone learns a library, right? So most of the times you don't know what you're supposed to do even, or what are the possibilities that a library offers, and you need to kind of search your way around learning that particular library. So if you want, you can code along. So we'll just write things from scratch. So I won't be showing any pre-written code. We'll be doing things on the go, right? So the first thing that I want to do is I want to generate a data set, right? So I'll just add it as so. This is what we are plan. We'll write the plan. So we want to generate a data set. Okay, and then train a model. Along the way, we want to visualize the loss function. Okay, train a data set for classification, right? So let me put it that way. Train a model, visualize the loss function along the way, and then plot the decision boundary. Okay, so this is what we'll do, or at least we'll try to do as many points as possible. And along the way, we'll figure out what functions to use, what libraries, what methods to use, and all that, right? So will this work for everyone?
Yes, sir. This is the best way, sir.
Okay, right. So I just start with plain NumPy, and so first thing I need to do is I need to generate a data set. So which means I need to generate some numbers, right? So how do I generate numbers? So the first thing that I will do is I'll go and search in Google, right? So I hope along the way you also, in case you are not familiar with this process of learning a library from scratch, I hope you'll figure out how to do this from now on, right? So you don't need so you don't need me at other stages in the process. So what I need to do is generate random numbers using NumPy, right? So this is what I want to do. Okay, so typically you will get your answer in the first 3 or 4 links. Here I kind of know what I'm looking for. So this random number generator is what I'm interested in. Okay, so I'll go and click this part and see what it has to offer. Okay, so if you notice in many of the code blocks in the slides, you would have seen this np.random.randn, right? Have you all seen that part?
Yes, sir. For integer.
Right. So now let's search this. This is also important to know good practices, right? So I'll just search for that same thing, right? Randint or random, right? If I search for this in NumPy, first link, okay, I'll go and click this. So read the second note, right? So look at what NumPy has to say. New code should use standard normal method of a default RNG instead of what is given there, right? So what NumPy is basically trying to tell you is don't use this, use something else. So use this standard normal method, and then it's saying something else here. So I'll see this thing. So when NumPy says please see quick start, it means that's a good place to look at, right? So this is how I'm going to generate random numbers. I'll just copy the whole thing, right? Usually this works. copying directly and then understanding later works. So I'll just run this, okay? Okay, so this is RNG is what? RNG is exposes you to some functions that will generate random numbers, right? So before I generate any kind of data set, let me first try to come up with the, let me first draw samples from the normal distribution, right? So that's what I want to do. I want to sample numbers from a standard normal, right? So do you all know what a standard normal distribution is? From your stats too, do you all know what
Yes, sir. Mean zero, standard deviation 1.
Right. So mean 0, standard deviation 1. So I want to generate numbers. Okay, so let me not make this too complicated. So I from numpy.random you are importing this, right? So this is the same as saying RNG equal to np.random.default_RNG, right? I'll get rid of the whole thing here, and instead I'll just have this. Okay, so this is a piece of code that you'll have
to import the randomness.
That is how I'm instead of importing random, what I'm doing is np.random.default_RNG. I'm using this. Okay, so I think what you said is correct. So how did this?
Yeah, just write import random.
Correct. Yeah, I'm sorry. Let me copy this. Okay, I think we'll stick to this.
Excuse me, sir. May I add something?
Yeah, please.
Actually, the way you did earlier was correct, basically. So the second line could be removed. Could you please go back a little bit?
To the earlier version?
Yeah, exactly. So the third line is no longer required, right?
Right. So I can just...
Yeah. So that's enough. The brackets are missing.
Good point, right? So I can just have this.
That's it. Okay,
right? So what we have done is we have... Okay, this is new, so don't worry. This is not very important, but this is good. This is a good practice to follow, right? So I am trying to generate numbers from the standard normal distribution, right? Let me first generate one number and see how it works. Okay, I have generated one number, and that turns out to be 0.4, right? If I run this again, I get a different number. Okay, I get a different random number from the same distribution. So I want to kind of standardize this, right? So I want my experiments to be repeatable, right? This is a very important, rather reproducible. Forgive me if my spelling is wrong, but in ML, this is a very important step, right? When you run experiments, when you actually, talk to your client or when you publish papers, since a lot of ML algorithms are probabilistic in nature, you will keep generating random numbers, you will keep working with probabilities, right? So you need your experiments to be reproducible, right? So I need to get the same values whether I run the experiment the third time or the fifth time or the 10th time, right? So currently I'm getting different random numbers, so I need to kind of introduce that reproducibility here, right? And I do that using a seed value. Okay, so now if I run this, okay, no matter how many times I run this, I'll get the same random number. I hope you all see this. Okay, so this is step A. So now what I want to do is I want to generate a lot of these numbers. So let's say I want to generate 100 such numbers. Now all these 100 numbers come from a standard normal distribution. Okay, so step 2 is once I have ensured reproducibility and I'm able to generate numbers, I want to plot these and see, right, how they look. So for that I need to import matplotlib. Okay, so I import that. Okay, so again, at this stage, I want to plot it. So can someone tell me what would be the right way to plot this? Not the code part, but what technique will you use to plot? How will you plot this?
Histograms.
Right, you will use a histogram, right? So what I'll do is I'll again do a search for, okay, so this will typically take you to the right links, so you don't need to worry a lot. So see, they have even this random number generator they give you, right? So this part we have already done. So there is this command called hist, right, where you pass the distribution and you give the number of bins as input. That is what I'll do here. So I'll say plt.hist, right? X is the distribution. For now, I'll forget about the bins, right? I'll just plot this histogram. Okay, something like this comes up. So see this, whenever you get some output like this, if you don't want this output to come, what you have to do is you have to add a semicolon at the end. Okay, so this is to suppress the output that comes below. Okay, so I have generated X, I have plotted the histogram, but this doesn't look so good. So I want to have more number of bins. Let me start with.
Sir, could you repeat that semicolon bit?
Yeah, so see what happens is, so there are two things in collab. I don't know how many of you know this. Whatever is the last command in the collab in a block, right, in a cell, that particular thing will be displayed. So for example, here I didn't say print of X, I just wrote X and this X got displayed.
Okay.
Okay, if you want to suppress this, you have to add a semicolon after that line.
Okay.
Okay, so that is what, for this also the same thing will happen. So I don't want this message here. This is basically what is returned by plt.hist of X that is getting displayed. I don't want this. So I just do this semicolon. Okay, so now let's begin by adding more bins. So plot this histogram with 10 bins. Okay, still okay. By default, I think it was something like 10. So this is no longer, this for now, this is not looking like a normal distribution at all, right? So let's add more data points. Okay, 1,000, maybe 100,000. Okay, and now let me increase the bins. Okay, now it's looking more or less like a normal distribution. What if we add 1 million data points? Right? So if we have 1 million data points, this is more or less like a normal, standard normal, right? Mean 0, sigma equal to 1. So, okay, so we are getting started with plotting. Okay, so the next step is I want let's say I make two observations regarding my plot. One is I don't want it to be rectangular, right? So I want it to be a square plot, right? So that is one thing that I want. The next thing I want is I want a title for my plot. That's the next requirement. Third is I want these numbers to be bigger, right? Currently these numbers are kind of small and I want them to be bigger. So there are three requirements and we'll see how to satisfy all three. The title is the easy part, right? So we'll just add a title. So if you search for that, you will come to know that this is the way to add a title to your graph. So standard normal, right? So okay, I've added a title. The next part is, these are my requirements, right? Increase font size, make graph a square plot, right? Make it a square plot. Okay, so for this, these are things that have got to do with the configuration of the plot, right? So matplotlib has something called RC params, right? This is been very useful. So this is called RC params. The full form for this is runtime configuration parameters. Okay, so you will see why this is useful, because let me just run this once and I'll show you what it gives you, right? So this RC params is actually a dictionary-like object, right? It's a dictionary. If you notice, there are some keys and there are some values. Okay, so there's something called font size. So font.size, currently it is at 10. I want to make it say 15.0, right? Now
those values that it is showing are all the default values, is it?
Exactly, they're all default, right?
Okay.
So I'm making it 15. Okay, so this is it has changed, right? So this is something I wanted. The next thing I want is my graph. I need it to look bigger, right? Sometimes it becomes difficult for us to parse what is happening. So how do you get the, so I need a list of all RC params. So what I'll do is, what is the, okay, so see, this is typically what you should do. You should learn to do on your own, right? No one, okay, we are reading an old version. You have to go somewhere else. See, this is something that typically no one teaches, right? And you have to go around and do this business. I'm doing it live so that you get some idea of how to do it, and that it getting stuck is not a problem, right? So let's see.
Sir, here you are knowing RC param is a parameter from where you can get all the parameters. But what
Right.
if we don't know the RC param exists?
Good point. So see what I mean, how I came to know this is, see, I did
overflow.
Yeah, so I asked for this question, increase font size in matplotlib. So first question is answered here. So they mentioned that alternatively you could use RC params and update this. Okay, so then the moment you know this, and it's not just for font size, but I can also do this for figure size, right? So that is how you, yeah, as someone said, Stack Overflow is the point of entry for many things, right? So I want to change my figure size to be something else. So let me change this to, say, 10 cross 10. Okay, it's a dictionary. I'm updating the key of a dictionary. That's all I'm doing. Okay, so this is easier to look. Maybe 10 cross 10 is too big, so I'll just settle for, say, something like 8 cross 8. Okay, so now I'm done, right? So I'll not be messing with RC params anymore, at least not at present. Okay, I hope you all got what we are doing till now. So this is just a brief introduction to plotting. Now where were we? We wanted to generate a data set, right? So let's go ahead and
in this plot, we can define all these fig size and font size. That plt.hist, inside that, if you do this, will it work?
Inside which one? Hist.
Yes, sir.
No. So see, what we are trying to do is we are doing this globally, right? So I'm for all my graphs, I want certain configurations to happen. So this is like a global setting, right? So I want to do this once, and I don't want to worry about this for all the other plots. So everything will follow this 8 cross 8 size, and in all my graphs, my font size will be this big.
In one of the lecture videos of week 6, sir has used another thing of percentage matplot or something like that. What does that mean? I mean, somewhere
okay.
he has used that.
Yeah, you're right. So don't worry about that, right? I also don't know what it is, but you can maybe that is for some other day, right? But not now, right? Don't worry too much about that.
Okay.
I think it is to plot these things here in the notebook itself. Sometimes it, like if you run locally, what happens is that another window pops up with the graph.
Okay.
To suppress that and make it inline in the notebook itself, you use that.
The percentage inline, right? Okay.
Percentage is just the magic symbol, right? To have commands in the node in Python.
Oh, is it? No, I'm actually not aware. I am like so whatever minimal requirement is there, that is all you know. So anything extra you can contact Vishwajit. Is it fine?
Yeah, I mean, I'm also doing exactly what you're doing live right now. Like I Google.
Okay. Yeah.
Like not right this now. Like I've done this before. That's why I'm telling this. Like inline, especially. I had the same problem I encountered when I ran it locally. It popped up in another window.
Oh, right. Okay.
Jupyter Notebooks, it does that.
Yeah. Right. In Jupyter Notebook. Yeah. So I was working on Jupyter at the time.
All right. Okay. So see this is good that you brought this up. So the philosophy here, at least for the remainder of the next half an hour, is we'll try to stick to as so some kind of minimalistic approach is what we aim for, right? So for example, we have used Seaborn in our collapse. We are not going to touch Seaborn at all. So all this should be doable with just matplotlib and numpy, and we'll just try to do that. Okay, so the important part now is how do you generate a data set. Now we'll see why RNG this thing is useful. So I'm going to generate these blobs, right? So for that I use something called multivariate normal, right? So there is no multivariate. Okay, we have a multivariate normal distribution. This is just an extension of the normal distribution, but for multiple variables. Okay, so we have, let's say the mean is at 0,0. And so do you all know what this distribution is? Have you been taught this in Stats 2 or any other course?
Yes, sir, we have been taught in MLF.
MLF, right? Okay, good. So you have a mean, you have a covariance matrix. So I'm going to generate I'm going to draw samples from this distribution. I'm going to draw 100 samples, right? You will see why I'm doing this. So let's see what this shape is, right? There are 100 samples that I'm drawing, and each of these samples has 2 dimensions, right? X1 and X2. So that is what this is. So 100 cross 2, and I'm plotting this, right? I'm drawing a scatter plot. So once I draw this, you please tell me if you understand what I have done or not. Okay, do you all see what I have done here?
Getting both the pictures.
The first feature and the second feature is used.
Yeah, the first feature and second feature I have plotted, right? So that is what I have done, and I've done this for all 100 points. Now you won't get this picture if you zoom in so much. So you have to zoom out. I want to make this axis somewhere between -10 and 10 on both the X and Y axis. I want to increase that limit so that I can see what is happening. For that I use plt.axis, right? So what does this do? You can again search. If you search Google, you will end up with this matplotlib.axis. So again, you must not get lost in all this, but if you choose the right link, you will know that with this you can set the X and Y axis limits, right? So I want to set it as -10, 10 for both X and Y axis. Okay, earlier it was some default value. Now it is changed to -10 to 10 on both sides. This is how you do it. Okay, now let me add, say, 1000 data points, and you can see that you are getting one blob out there, right? This blob is centered at 0,0 because that is what I said the mean was. And since this covariance matrix is identity, it comes out as a nice circular blob. Okay, is everyone with me so far?
Yes, sir.
Okay, now let's say this is a blue color blob. Okay, and I want, these are my positive data points, so I'll call them x1. Okay, now I want another set of blobs. They are the red color blobs, right? And so if they have the same mean, then I can't differentiate the two, right? So let me push this to 3, 4, and let me push this to minus 3, say minus 5 or minus 4. Okay, so I'm not plotted the 2, so let me plot x1 first data point, and this will be my second data point, sorry, second class. Class 1 is blue, class 2 is red. Okay, I think we are doing this twice. Okay, so we have our data set now. So did everyone understand what happened so far? How did we generate these two blobs?
Yes, sir.
Okay, so this is how we generate these two blobs. And now what we also need is, by looking at it, it's clear that this is one class and this is another class, but we also need to label them. So let me call the blue color class label class 1. So I'll add this label of class 1 here. And then the red color ones, I'll call them class 2, right? So I've added the labels, and the moment you add a label, if you want these labels to appear in the graph, then you need a legend. So I add that using plt.legend. Okay, so that is how you generate a data set and then add the legend out there.
So how do you increase the number of features by the increasing the mean array?
Sorry, how do you change the mean? Is that what you're
how do you increase the number of features? We've got 2 features in every class. So
right.
If I want to increase the features, then in the mean I have to keep adding more numbers, right?
Yeah, you'll have to keep adding more numbers. Unfortunately, we won't be able to visualize that. Right. So that's the only problem. Otherwise, yeah, that's how you do it. Your mean vector changes. And okay, so
how do we graph the PDF of the as a surface, as the professor taught in the visualization of Gaussian NB classifier?
Okay, so we won't be able to do that today. We'll I think given the time that we have, we'll only be able to do say something along the lines of visualizing the loss function and plotting the decision boundary. That before we get there, I think we'll have a lot of work to do.
Okay, thank you.
Okay, so this is class 1, class 2. So you have your data set.
Sir, is it like a Gaussian mixer model?
I won't say this is a Gaussian. We are only generating data sets, right? We are not modeling. We are just this is a toy data set, right? We just have a toy data set to work with. Okay, so now comes the important part. So your X, remember that each one has a shape of 1000, 2, right? There are 1000 points and the number of features are 2. So this is, you need to put them together into one feature matrix. Okay, so one way to do this is to concatenate these two arrays, right? X1 and X2. You can concatenate them along the axis 0, right? Along this 0 axis. If I do that, I get 2000 points, each having 2 features, right? So this is my feature matrix. I hope this part is clear.
If you do it along axis 1, it will be 1000, 4.
We will do that and see. Yes.
Okay, got it.
Okay, so X is your feature matrix and I need y's, right? So let me go back and let me add the labels here. So y1 is I've called it class. Let's call it class 1 and class 0. So I need a set of ones, right?
So this axis 0 is actually rows only, sir, along rows.
Along the rows, yeah.
Right.
That problem we still have. Let us come to that in the end. So okay, so this, do you all agree that this is how you do the labels? You need a set of ones. You need as many ones as there are data points. Is this
Right.
part clear? Okay,
Yes,
so
sir.
likewise we'll do for y2, and it'll be just zeros, right? So x2 dot shape of 0. Okay, so the way you make your code slightly better is you also fix the number of data points. Let's say you have 1000 data points. You don't want to keep, you want to make your code slightly better, so you just change these to variables. Nothing changes, but it's slightly better now. So that is x. Now y is slightly simpler. I can just directly concatenate them. I don't even need to specify the axis here, right? Sorry, this has to be a tuple. Okay, so far is everyone clear how we reached this stage?
Yes, sir.
Okay, so all right. So now what we do next is we need to divide this into training and test, or train validation test, right? So I think you all know what that is. So we have to use sklearn here. From sklearn we import
test split model, something like that.
Yeah, we use the train test split, right? So okay, so now if I want to know, see, let's say in the exam, right, you don't know what the parameters are. So you have to pass x comma y, but you also need to know the fraction in which you have to split, right? So you can use this function name and question mark, right? So when you do that, you will get this help. Okay, so I hope you're all aware of this.
So in this,
we are doing in portal. Is it available there also?
Yeah, it will be available there also. In portal, what you'll have to see for MLP, the exam will not happen on the portal. So for MLT, it will happen on portal. Then what you have to do is okay. So there is, let's see, for that, what do you do?
you'll have to subset the x and y, I think.
No. What I mean, so the question is, how do you get this help on the portal? Here you can do this, but on the portal, okay, that's a good point. I'll get back to you. There is, I don't know if you have if you do help, you won't get for anything. You'll only get for inbuilt function.
But can we use sklearn in the MLT exams?
No, sklearn no. No sklearn in MLT, only in MLP.
But model selection here can use, right?
That you
train test split.
That you can, yeah. This you can use. Train test split you can use. Okay, right. So train test split takes what as input? The x comma y. So let me just.
So we can do random dot random, generate a random number between 0 to 1, and for each observation. So we can do that just using the.
Yeah, we can use.
Function.
Yeah. We can do that, but this is, since this simplifies stuff, I'm just using this. So they have given one example also. What is
test size?
Okay, let's say test size is 0.2. They return this, right? I'll just directly copy. Okay, so I also want is by default the data set is shuffled, right? So I want to retain that. I don't want to disturb that. So let's see what we get.
Sir, you should mention a random state.
Okay, let me use the same 42. Okay, so I'm pulling these to the next line so that my code is more readable, right? So there are say 1600 points, and white train dot shape 1600 comma, right? So it's a vector, label vector. So I have my ingredients ready. I have I've generated a data set for classification, right? So far that is where we are currently. Okay, so is there anything that you would like to ask at this stage, or shall we continue?
Continue, sir.
Okay, all right. So now comes the tough part. So see, I'm going to do logistic, like we are going to do logistic regression. Okay, so logistic, that's what we are going to build, right? We are going to build a logistic regression model. Now I'm not going to use classes, right? Classes come much later. So from where do you start, right? So you basically use functions, right? Whatever functions you need, you try to write them, and then you turn your functions into methods if you are using a class, right? So this is, so I don't know what approach I'm going to take, but let's see, right? So in your exam, right, when a question comes up, right, you have to train a logistic regression model. So the first thing that you must be absolutely clear about is the equations, right? So if you're clear with your equations, then half your problems are solved. So two equations that you would need are the loss function. The other one is your gradient, right? So this is your gradient of the loss with respect to W, right? You need these two.
And the predict, right?
Right. And the way to predict it, right? So what do you call that? Let's say you need to know what, right? You need to know how to predict it, right? So which part is easy? Let's say, so tell me what to start, where to start. Can someone tell me where to start?
I would start with predict.
Okay, we'll start with predict. So for predict, what you need as input? Some matrix, right? So some matrix, let's call it X, right? That's all, right? You don't, let's say you don't have any access to anything else. So
and the weight vector also.
Okay, that is also needed. So if I have X and W, then this is sigma, right? Sigma of, this is the equation, right? Linear combination, and then sigmoid of. Okay, so I'll just write it like this. I'll just say sigma of X at W. This is matrix multiplication. So you need to be absolutely clear about what your dimensions are. So let me write that as a comment here. So X is, let's keep things simple, 100 cross 2, right? Assuming there are 100 data points, X is 100 cross 2, and W should be, okay, you need to add this dummy feature, right?
Yeah, 3.
So we put this as 100 cross 3, and this is 3 cross 1. Okay, so that means XW would turn out to be 100 cross 1, right? So you have 100 data points. XW is the output or the predicted value of the linear combination of these 100 data points with the weight vector. Okay, so clearly I see that I need to write the sigmoid function. So let me go ahead and do that. That is one helper function I need. So if I pass some z value into the sigmoid function, what should I return?
1 over 1 plus
1 over 1 minus e to the power.
Yeah.
Right. So this is the sigmoid function, right? So again, it may be useful to, okay, I don't want to write this, it will take some time. But I think you all know what this is, right? 1 by 1 plus e power minus z. This is, so sigmoid is now taken care of. Okay, so
threshold also. Threshold 0.5 default, or maybe we can customize it.
Right. So see, this is returning. This will return what? Probabilities, right? So let's divide this into two parts. Sigma of xw is the predicted probability. So I'll call that predict underscore. Okay, and what I actually predict is I first get my probabilities. Okay, and so I now need to make a prediction. So how do I do that? Wherever my probability is greater than 0.5, you have to return 1. If not, you have to return 0.
A threshold.
Right. So you look for all those places where the probability is greater than or equal to 0.5, or let's say a threshold is fixed. For those values, you return 1. For all other values, you return 0. Okay, is this fine?
Yes, sir.
Okay, so now let's say the prediction part is taken care of. So
can I ask an ancillary question?
Yeah.
Associated with this. So here in sigmoid function, we're doing 1 divided by 1 plus NP, right? This NP exponential of minus Z is an array.
Correct.
And we're simply adding 1. So in this case, 1 gets broadcast
across all the
array.
Yeah.
Okay. Whereas if the array is like a bunch of columns, then it doesn't get broadcast. That portion of it, I mean, if you want to talk about it, we can, but otherwise we can skip and go through. Because that seems to be a little confusing for me also, where it gets broadcast and where it doesn't.
Okay. See, typically for scalars, if you have a scalar right like this, then that gets broadcast across all the entries of your array, no matter what your array is. So if your array is something like, say, 1, 2, 3, 4, 5, 6, and I do +1, it'll be 2, 3, 4, 5, 6, 7. It will get broadcast across the whole thing. Okay. Right? So for most of the expressions, see, that's the power of NumPy, which is that almost all mathematical expressions directly get translated into their NumPy form without having to do any adjustment. Okay, so slightly tricky thing is when you try to add. So when you try to add something like this, right? So broadcasting becomes a pain when you want to, let's say, add a row vector to
a matrix.
Yeah. So this is 3 cross 2, right? This is a 3 cross 2 array.
Right.
Now it will throw. I think it will throw an error if I try to add 1, 1. No, 1, 1. Will I get an error? Let's see. 1, 1. I don't get an error. If I try to add 1, 1, 1, then I'll get an error.
Because the dimensions don't match.
Yeah. So if I still want to add, I think I'll have to do something like this. Right. So I have added 1 to the column. So 1 becomes 2, 3 becomes 4, 5 becomes 6. Right. So that this broadcasting can be slightly tricky, but we will come to this.
But just to understand, the scalars will just simply get added.
They will get simply added. Yeah, they will get, so scalar, no worry at all.
Okay. Because I was trying to do NP ones off and adding and all that.
No, yeah.
This becomes easier.
Right. I saw your code on, that part alone, you can change that ones to just a simple scalar like this.
Okay. Thank you.
Okay, right. So predict is done. So this part is done, y hat is done. So before going to the loss, let's finish the gradient, right? So gradient is actually quite simple. Grad, you need x, you also need y, you also need w, right? You need the whole thing. So x transpose into sigma of xw minus y. This you have to mug up, no other go, but it's not very difficult, I would say. So x transpose, see x transpose, you don't need to do np dot transpose of x, just stick to x dot t, that will work, right? X transpose into xw sigma of xw, right? So sigmoid of xw minus y, that's all, right? This is your gradient. So you see how simple it is to translate from mathematics to NumPy. It should be as simple as this. Okay, so did everyone get this part? I have just, whatever was there in the formula, I have just simply put it in terms of NumPy expressions.
Yes, sir.
Okay, so this is grad. Now I write. So what do I need to compute the weights? To estimate the weights, I need to do gradient descent, right? So let me call it. Actually, let me not call it gradient descent. I'm actually fitting, right? So this will probably come as a part of the fit method. So okay, so I'll just write the update rule first so that it becomes simple. So how do I update my gradients? W equal to anyone? What should be my weight update rule?
So W0 minus learning rate.
Okay.
And multiply by the
gradient
slope.
Right. Okay. Right. So this is the update rule. Now this is for one epoch, right? Assume that I'm doing this whole normal gradient descent and not mini batch or anything. So I need to do this for certain number of epochs, right? For so for
you'll have to put LR in the parameter.
Right. So let me also put epochs here. So LR epochs, right? Let's say default is 100 epochs. Default learning rate is 0.1. Okay. So for underscore, right? Underscore, I know, I hope you all remember this from Python. If you don't want to use a loop variable, you can just use underscore. So for each epoch, update the weights. Okay. And finally, you return the weight. You return what? Do you return the weights? We'll worry about returning part later on. Okay. So correct. This is how you fit the model. Okay. So fit is done. Okay. Let me just, for the sake of completeness, return the weights for now. And then
sorry to be pedantic.
Yeah.
Sorry to be pedantic. I mean, fit is being used for normal equation. I guess it's okay. It's only semantics, but fit in the class X is being used for normal equation.
Right. So see, the reason I'm using fit is again, the reason is see there is, if you look at say any sklearn class, right? So this is sklearn's fit method. I believe they have these two main methods.
Yes, sir. Fit and predict.
Right. So fit and predict. So CLF dot predict dot fit, right? So this is what we are trying to replicate. So if I pass my data set to the fit method of the classifier, it should fit the data set. Sorry, it should fit the model to the data set and then predict.
Oh, I guess because for logistic regression, there's nothing called normal equation. I guess fit works for
right. Yeah. Okay. So fit and predict we have. What else do we need? We need to plot the loss, right? So we need a way to calculate the loss. Again, I'll have to pass my data set and my weight. So see, this is this minus, again, this is something you have to remember, minus y into log y hat, right? Minus 1 minus y into log 1 minus y hat, right? So this is the formula. Y hat is nothing but the prediction, right? So this fellow here. So that is my probability basically. So let me not. So this part is clear, right? What we mean by y hat, sigma of xw. That is what y hat is.
Yes, sir.
Okay, so just one thing we have to be careful here is when we say y hat is this, xw, sigma of xw will return 100 cross 1 array. It will return a 100 cross 1 array, and y will also be 100 cross 1 because there are 100 examples. Let's say that is what you're training with. So this is finally an array. This is not yet a loss. This is an array of size 100,1. So you'll have to sum the loss for all 100 examples. So you just do np.sum and return this.
Can you explain the last part again, sir?
Yeah, so what we are doing is predict, if you recall, returns the probabilities for 100 training examples, right?
Right.
So this y hat will be an array of size 100 cross 1.
Right.
Now y is also an array of size 100 cross 1. It's the labels for the 100 training examples.
Right.
So when you do y into y hat, in y into log of y hat, this is 100 cross 1. This is also 100 cross 1. So it's a vector. So what you have is a vector where each element of the vector is the loss for that particular training example.
Right. Okay.
So you're summing the losses. So this is the sigma.
Right.
Okay. So this is loss. So now we have most of the ingredients. So we can just. So now we have now from now on it's fill in the blanks and then debugging, right? So for example, we have to start with zeros, right? So you have to initialize your weights. So x dot shape of 1, right? So if x is a feature matrix of size 100 cross 3, then I need 3 weights, right? So that's why I use x dot shape of 1 and not x dot shape of 0. Okay, so in all this, we have not
Fit
yet.
will not have a w parameter, right? Because we are initializing w.
Yeah, good point. We don't need w, right? So fit should not have w. It should be like, yeah, as you said, it should be like exactly, it should resemble this. It should have only x comma y, and these also should be default arguments and not. Okay, so w is like this. Now one thing that we are missing is adding a column of ones, like the dummy features. So we need a pre-process step. Let's add that right at the beginning. If I get a feature vector x of size 100,2, I need to add a column of ones, right? So see, there is one way to do it. One is to stack columns. This is stack columns, right? You stack all ones. Let me say that n is the number of examples, right? So there are 100 examples, so that will be stored in n. So I first get hold of a column of n ones, right? A column of ones. That is this one, right? Let me just. Okay, so and then I stack it to the left of my feature matrix x. So 100 cross 2 becomes 100 cross 3.
So for left, you wrote it on the, like, is there a difference if you want it on the left or if you want it on the right?
Yeah, there is a difference. So I mean, so there is not much of a difference in terms of computation, but I would like it to be left because I want my features to be like 1 comma x1 comma x2 rather than x1 x2 comma 1. That is all. That's the only reason.
So the bias that we interpret on W will be number 1, right?
Number 1, yeah, that will be the number 1. Yeah.
No, I meant, sir, is there a difference that we do in the syntax in the line of code?
If we swap these two, you're saying?
Yeah.
If we swap these two, then what will happen is it will turn out to be x1 comma x2 comma
okay.
1.
Yeah.
Right. So we have to so this is what we are returning. Now we have so the small pre-processing that we do by returning a 3 cross 100 cross 3 matrix, right? So now pre-process. Yeah, I think we have most of the ingredients. Right. So let's start the training. I don't know. We'll have to do a lot of debugging, but let's. So pre-process of X. Let me just repurpose this as. So I start with the X train data set, right? And I just pass it and then I reuse the same variable name. I hope that should be okay. Right now. And then I directly call. Sorry. I want to fit X train, comma Y train with the default learning rates. I don't want to meddle with them. Okay, so now let's just run this and see where we get stuck. Okay, so you're obviously going to get stuck somewhere. Okay, it ran without any errors, but we need to debug, right? So we need to plot the loss and see what's happening. So how do you do that? In every epoch, you have to do that, right? So you update the weights and then you compute the loss. So, and then you store all the losses somewhere. So losses is a list and you append the loss for this particular case at this stage in the process. And maybe you return both the correct weights and the losses. Right, please stop me if something is not clear at some stage. Okay, somewhere we are encountering zeros, so we'll see. Okay, now let's go ahead and plot the X value will be what? It will be the number of epochs. So let me also fix that. Let's say the epochs are 100. Then are you aware of the arange function for Numpy?
Yes. It will generate the integers from the given range.
Right. So there are, in case you have not seen it before, so np dot, just like the range function in Python, np dot arange will give you the sequence of integers from 0 to n minus 1, right? So on my x-axis, I have these values, 10 epochs. On my y-axis, I have the loss values, right? This is all I'm plotting. So it will be a horrible looking curve is what I hope. Okay, nothing comes up. Okay, so we'll have to debug now. Okay, so epochs, let me start with the. So in such cases, what we do is we first manually look at this list, right? And see what really is happening. What are the values?
Sir.
Yeah.
So in the graph, nothing was happening. Then how did you configure that what is missing?
Yeah. So that's why what I'm doing the next step is I'm looking at the losses, right? So nothing, the loss, if you see, they're all nans.
Okay.
Right. So it's like some 1/0 kind of thing somewhere it's happening. So what we'll do is we'll try out a few things. The learning rate is probably high. So let me first reduce the number of epochs so that It's a manageable size. Epochs is 10, and let's say the learning rate I set to be 0.001, right? And when I fit, I pass my learning rate and epochs. Now let's see if it improves. Okay, so the learning rate kind of seems to help. So let's now go for more number of epochs.
So reduce the learning rate to the 0.01.
Okay, we
yeah.
Okay, I again end up with nans. So okay, I again have nans, I believe. So let's see. Okay, so do we have these nans right from the beginning, or does it start off with nan? Because if it starts off, then we might have some problem. Okay, I'll go over this code once, and if someone is able to find out the problem, you can suggest ways to debug.
Sir, in y hat we want the probabilities, right? Not the labels.
In y hat, correct. We want the probabilities. So that is why I've used predict underscore, right? Instead of predict. Sigmoid of xw will give me the probabilities and not the labels, right? Okay, so yeah, y hat might be the problem. Good point. So see, log of 0 is typically where you get nan, right? So this is, so if you notice, if I do np.log of 0, I get minus infinity, but so the problem might be with this step. Okay, so the problem might be with the loss here. Y hat is
so in this, if you go to the predict underscore,
yeah,
we are saying x, the shape is 100 cross 3.
Correct.
Right now that 100 cross 3 is coming from the pre-process.
Is coming from right. So okay, let's first verify that whether it is correct, whether it is 100 cross 3. So I am at the, how do we debug this? So I am at predict, and I'm printing the shape of x. So let's now make it very simple. I am just doing one epoch, right? And whatever I get should be, wow, saying 1600 cross 12. Okay, do you see that? So this is, every time I run it, something else comes up. Oh, okay. So do you all see what is happening?
Xtrain is just getting added.
Right. So Xtrain is just getting, so that's the problem with the collapse. You should be very careful. Okay, it's a bad idea to use the same name. We'll just call it X, no? We'll just call it X, and okay. So in such cases, right? So what you have to do is you will have to restart the runtime so that all the variables get, erased. All the memory gets erased. And did everyone understand what was happening? Okay, I think it's
no, sir, I didn't understand actually.
That variable was you use the same variable on the left and the right hand. Was that the problem?
Yeah. So I used the same variable name. So because of this, a problem because of two reasons, right? So every time I run this cell, right? See, if I run this cell, then Xtrain, if it's initially 100 cross 3, then Xtrain now becomes 100 cross 4 because I've added one column of ones, right? Now, if I run this cell again, what happens is Xtrain is currently 100 cross 4. So it will become 100 cross 5. So that is what was happening. Every time, this one column was getting added. That was the problem. So the way is to make a clean. So restart and run all. That is the way to, and of course change the variable name to X. So I just want it to be slightly easier on the main, not have. Okay, I'll just call this X comma Y, right? If it is fine, I'll just call this X comma Y. The testing part is X test, Y test, but this is X comma Y. So that anyway, we are not going to use the test set now. So, okay, X comma Y is your training data set. So, but I'll end up with the same problem, no? Again?
Yes, sir. You'll have to call this something else.
I think you'll have to run the one cell above and this one a little repeatedly.
Pre-process we can exclude to the other shell.
Agreed. Yeah. So no. So I just want to see. I just want to keep running only one cell. So that might be, it's a good solution, but I just want to. Okay, let's change the name. No. I'll just call this xtrain underscore ytrain underscore. I don't know if all this is good practice, but for now we have time only for this. So where is this? So I'll just call this xtrain, right? And this is xtrain underscore.
You'll have to run that again, sir. That cell.
Yeah. So what I'll do is I'll restart and run the whole collab.
Right. So ytrain underscore should be given, right?
Oh, right. Okay, so I'll change this to ytrain. So this is very messy, but this is how it works. Yeah, actually, this is how we all work, or at least most of us work this way. So
you should start with the Numpy call, right?
Right. So I hope there are no other syntax errors. So it's restarting and running the whole thing.
Third, we have to X underscore train. W1 losses subject.
W comma losses where
X underscore train.
Good point. Okay. Okay, now let me run it a few times just to make sure that nothing is wrong with the. Okay, so this part we have fixed, right? So this is always going to be 1600 cross 3. Okay, so there is no problem there. So let me. So any ideas, anyone, why we are not able to fix this? Okay, so we are getting a loss of
increasing the number of extremism. Sorry to interrupt.
Yeah.
So I was just trying to replicate what we're doing here. So the increasing the number of epochs seems to help. So can you try doing that?
Okay, let us.
So for 100 epochs, I'm running it, and it seems as if it is getting something.
Okay, so let us.
Seems like a normal loss curve, but I don't know if it is correct or not.
Yeah. Good point. So let us know. We have run it for 100 epochs. Okay, that seems to fix the problem. Okay, so this seems to be. So I think we are learning something here. So let me go back. Why are these things not getting updated? My graphs are looking very small now. Okay. Okay, right. So this seems to be good. So let me go to a new cell and see what the final few losses are. Last 5 loss values are. Okay, there's still some considerable loss. So maybe let's see if we can increase the learning rate to 0.001. No, that doesn't seem to work. Okay, so see, so far we at least know that the model is learning something, right? So the next step would be to see how the predictions look like. Say, let's just run it on the train data. we have to pass x comma w. So predict of x train comma w. This will return what? This will return some set of binary values, right? So I want to now compute the accuracy, let's say, right? So let me add one more function. So I want to compute the accuracy. So y train and y predict, right? So if I have these two, can someone tell me how the accuracy function will look like?
So we'll have to count the true positives
to do
and
np
true
dot where
negatives.
x train is equal to y predict.
Okay, so I'll just do np dot where these two are equal, right? So
right. Then you give it 1, otherwise 0.
Right. So now this will be a binary, again a binary vector of ones wherever my prediction matches. So I'll just sum this, right? I'll just sum this. Right. So this is the total number of correct predictions. I divide this by total number of examples, right? How many? This will be what? Y train dot
0.
Yeah. So this will be if I look at the shape of 0, right? So this is my accuracy. I'll just multiply it by 100. And I don't want too many numbers appearing. So I'll say accuracy is this, and I'll return. How do I return this? If you remember this f strings, it is f string, and I think this will return 2 decimal places after the whole thing. So I am not very sure, but let's see. So now I have accuracy. So this is y predict, right? This is the predicted label. Now I want to compute the accuracy of this. I pass x, y train and y predict. Okay, it says 100. It's maybe, what is it on y test? Okay, can someone tell me why this is throwing an error?
Sir, here we
dummy feature not added.
Array dummy features.
Right. So we just do a pre-process of x test. Okay, so this is, so the model is working. So it's a too simple an example, right? So obviously it's going to learn. So what we let's final part alone, let's do and close, right? Let's plot the decision boundary, and then we'll close. That will be like the last part. So let me copy the data set here. Okay, so I copy the data set, and so this is my W, right? If you recall, this is the weights that I have learned. So this is of this form. This is of the form W naught plus the model is of this form. So the decision boundary will be W transpose x equal to 0, right? Which is the same as W naught plus W1 x1 plus W2 x2 equal to 0. Okay, so how do you plot this in Numpy? In Matplotlib, you think about this as x-axis and this is y-axis, right? So I need to do something like this. X2 equal to, bear with me, this will be some, I need to get this as a fraction, and that's why I'm doing all this. Is this clear? X2, I write it as y equal to mx plus c form, right? So y equal to m will be minus w1 by w2 and c will be minus w0 by w2. I hope everyone is clear about that part.
Yes, sir.
Okay, so now now what I do is, so till this the data set, now decision boundary. So I first get hold of x values. So x, let's say, goes from minus 10 to 10. So this is done using something called line space. Okay, line space have you all encountered before?
It's encountered, but not very clear on what it does.
Okay, so actually it's a very simple function. So np dot line space of -10 comma, let's first do something like this. So this is
comma 10.
Okay, so something else. Okay, what I'm looking for is something that will give me simple numbers. So how many are there? 1, 2, 3.
You could do 0 to 9 with 10.
0 to 9 with 10, huh?
Yeah.
Super. Okay. So what this is doing is this is dividing the interval 0, 9 into 10 equal parts, equidistant, equally spaced parts, right? So 0 to 1, 1 to 2, 2 to 3, so on, right? So if I do it as 20, then I'll get 20 points, but equally spaced between 0, 20, 0, 9.
Yeah, okay, sir.
Okay, so now what I want to do is I want to divide my interval -10 to 10 into say 100 parts, right? It doesn't matter how many, -10 to 10 into 100 parts. And the function is, the decision boundary is mx plus c, right? So m is minus w1 by w2. So minus w1, okay, what is w1? W of 1, right, by w2, and m into x plus minus w0 by w2 minus w0 by w2. This is my y. Okay, now I just plot on the same graph x comma mx plus c, which is basically this, and I say that the color is going to be black. Okay, let's run this and see. Okay, so that's your decision boundary.
So this y, what is the w1 by w2?
See, this is your equation, right? Your w is w0.
This is clear.
Okay, so this
how did we get?
You're asking how we got this expression.
Yes.
And this is from this, right? So y equal to c plus mx, right? So w0 by minus w0 by w2 is your constant, and minus w1 by w2 is your slope.
Right. So this w is my weight vector, right?
W is the weight vector, yeah.
From the function.
Yeah.
Whatever.
Yeah.
Can we go up to the functions?
So when we fit, we return the trained weights, right, and the losses. So that w is what I take.
Okay, so that'll be in. Okay, that'll be shaped in 3.
It'll be 3 cross 1, right?
3 cross 1. Okay. Got it. No. Yeah.
Okay, so yeah, so that is what we get. So this is.
So while plotting that x comma y, it directly takes the first variable on the x-axis and the second on the y-axis.
Yeah. Plot of x comma plt dot plot x comma y will be, that is what it will do.
Yeah. Okay.
Okay, so yeah, so that is.
So can we bring the distance of these two clusters and be closer than?
That's a good point. Then it'll make the problem also slightly non-trivial. So we'll make the means say 1, 2. This is say -1, -1. How close are they now? Okay, so they are like too close. I don't want them to be
close.
I don't want them to be too friendly also. So okay, this is okay, right? Let's.
Yes.
This.
Now the accuracy should also not be.
Yeah. So if we run the whole thing, okay, I think we should print the accuracy and not. We don't need the. Right. So there is some 99.5 and.
Right.
Okay, why did this not reflect the change? Okay, I think we have to see. We just should use variables all through, not like this. Oops, I kind of overwrote that. It should come only till this.
Right.
Yeah. Okay, so yeah, I think that's all.
And we can make out why the accuracy is also there. You can see one blue point, two blue points, and one red point in the blue.
Right. Yeah. Right. Yeah. So see, you can now take this code and you can do all sorts of nice things. So you could probably add. See, you can change the covariance matrix so that maybe it will throw an error here because your covariance matrix is not positive semi-definite, all that it says. But if you use the right kind of values, you will get elliptical looking things, right? So all these things you can play around with, and yeah, maybe that's for a future.
So will we get this?
Okay. Yeah, I don't mind sharing this. I can.
Otherwise, we can recreate it from the lecture.
Yeah.
I started with coding with you, then I got distracted and I was just watching this.
Okay, sure. So I'll just, since we have this course level policy, I'll just check with the team once.
Right, sir.
And then I'll get back to you.
But this was very helpful, sir.
Yeah, this session was very good. I would suggest that we have this kind of thing every week, sir.
Yes, sir.
Yes, sir.
Yeah, sure.
Our learning curve was much better than the ones that was shown in the graph here.
Okay, sure. So
in fact, I cleared Python because of you, sir.
Same here, sir. It's the same here.
Oh, sure.
Arthik sir is our favorite.
Oh, right. That's sure. I'll just we'll try to make sure that all sessions are like this.
And sir, I assure you, once we will do 3-4 sessions, now we will our fundamental will get strong. So within after that we will be able to do by ourselves only.
Yeah, sure. Yeah, we will try to do more sessions like this. See, that's the point is at some level you should not need me or anyone, right? So if we can reach that stage, then it will be great.
No, so what happens is, I'll give you my Python experience. I used to watch you doing those activity questions, and then I used to go back and do it myself. And wherever I faced a problem, I would come back and see those videos and do it again. So that actually creates a good, the way of doing it, we kind of learn it pretty quickly.
Right.
So, yeah.
Also much simpler than the actual lecture problem. So this has whatever necessary. So it's easy to understand also.
Right, sure. So one suggestion going forward is for the exams, right? You don't need to write classes. Writing classes is good. So probably in Saturday session we can convert this into a class. See, class what you put one class logistic regression, and then you press one tab button and everything goes to the right. So you should add self here and there, but see what was missing and what you found difficult is that from where did the class come might be a question that you might all have had, right? So out of the blue, I think if you are presented with 40 lines of code, I feel it might be tough, right? So when you look at it incrementally, it becomes less foreboding, right? It's actually a simple code, right? Whatever we wrote.
Yes, sir. Now it seems very, very simple, sir.
And so the step-by-step process actually makes it simpler. When we are going through the lectures, it's already there and we're just reading through it. So it doesn't help actually. It's not very intuitive.
Right. Yeah. So see, Professor Mitesh, I don't know how many of you know Professor Mitesh Kapra. He's one of the professors in the CS department from IIT Madras. So mainly I should thank him for this, right? So if any of you has time, please go and watch his lectures. He has a lecture series on NPTEL for a course called Deep Learning. Right? Deep Learning is just advanced ML in some sense. Right? So
could you put his name on the chat, sir?
Yeah. So Mitesh, where is the chat? Okay,
his name is listed in the computer science department.
Yeah. So see, Mitesh, M.
Okay, got it.
Okay, so he teaches this deep learning course. Where is deep learning? Okay, I'm not able to find that page. Yeah, so Jan 2022, right? Currently, he's teaching this in IITM. Yes, the course that he taught in 2019 or something, he has recorded it. So recordings are available. So see, you should look at his slides. Okay, so a lot of this you will understand because this is all gradient descent stuff like that. So if you open any one of his lectures, right, he would have used this incremental approach. Every new slide will have just one new information on top of a previous slide. So for example, you see this process, right? So there is this slide has this information. Next slide, some new information comes in. Third slide, something more. So see, if you're directly presented this third slide, it'll be very tough because I need to go through these 5 snippets of information. On the other hand, if you start with this and then I show you this and then I show you this, finally I end up with this. So your processing capacity also is much better if you do it this way. Right. Anyway, so that is regarding.
Sir, how the exams will be? It will be like full implementation of one particular model or kind of PPAs?
It will be a mix of the two, I would say. So you should be prepared for both.
And it's kind how long it will be there and how many questions, any idea, any details?
I think it is for 2 hours and you will have like say 10 questions, maximum 10 questions for 2 hours.
Any choice of questions?
No. You would
all
have to
mandatory.
Yeah.
And any graphing also will be there?
No graphing. So graphing is tough to evaluate, right? So, but please do learn it. So don't.
Yeah, sure.
Don't skip it, but we won't be able to ask you any graph related questions.
Okay.
What would be the syllabus, sir?
I think first 5 weeks. Earlier in the last term it was 4 weeks, but then I think now we are comfortably past week 5, so it will be like first 5 weeks.
Okay, sir.
So do we need to book a slot for the OPE one?
Slot booking, I am not very sure whether it is. See, if it is happening only on one day, then you don't need to book a slot. If it is happening on 2 days, then there will be a slot booking. But I think you don't need to. But we need to confirm with the team.
Sure, thank you.
Okay then. So
one general.
Yeah.
Sorry, just one general. I think we struggled initially. At least I struggled to get a hang of was, see, there is this basic mathematics statistics that we learned in MLF. And then there are a bunch of models that are already presented in the course. And then on top of it, we have the coding that we have to learn along with Numpy and other things. So in terms of the expectation as to what we should know in order to be able to successfully clear the exam is one thing. And in the long term, what we need to know are two. It looks like there are two different things, right? One is we understand the models and simply implement them seems to be just enough for this basic course, for this course, I mean.
Right.
But the underlying mathematics and statistics seems to be quite deep enough. I'm not sure if we will be able to even understand all of that within the 12 weeks.
Agreed. Yeah. So see, this is what I have been feeling for a long time. So typically 12 weeks is tough. It's too short duration for any course, right? So unfortunately, you'll have to return to the content time and again. See, for example, as an instructor, right, I am doing this MLT for the second time, and some questions that you folks are asking are really challenging, right? So I am also like struggling to keep pace with all these new questions that come up. So there's no other go. You'll have to revisit the content, and maybe in the third attempt you'll understand a much better chunk
Right.
of the subject.
Sir, will you be there for the next of these weeks? I mean, for rest of these weeks.
And not all weeks. I'll be there for few of the weeks. So week 8, week 11, week 12, I think I'll be there.
So week 7, you will not be there.
I may not handle week 7. Right. So I'll be
The
there
previous approach of having activity one person and the practice one person, something like that you used to do before, I believe. That approach was better, I feel.
Okay, for Python, yeah, we did that. So
yeah.
Okay, we'll try to see if that can be done.
So there is a sync between all the weeks. And now what happens is every week there's another person coming and there's no sync between those 2 weeks actually.
Agreed. Yeah. So yeah, agreed. So one person should be involved in all 12 weeks. That is much better from a learning standpoint. That is better. So okay, we'll try to see if that can be done for the remaining weeks.
Yeah, thank you, sir.
Please try to do it by yourself, sir. I mean, we want you to take our classes, sir.
Right. So yeah, we will try to arrange to the best extent possible. We'll try to arrange. Okay.
We can send you Horlicks and Bonvita if you require.
Okay. Yeah. So yeah, thanks a lot for joining. I think it's pretty late for some of you, I believe.
Thank you, sir. Thank you.
Thank you so much, sir. Thank you. It's been very
Thank you, sir.
Thank you.
Thank you so much,
Thank you, sir.
Thank you.
Thank you.
Thanks everyone. Yeah.
Thank you, sir.